Alright, so in this video we will be talking about the kinetics of enzymes, and this just means that of course since enzymes quicken up the pace of a particular chemical reaction, then the reaction must take place at a particular speed. And this speed, this efficiency by which the enzyme speeds up the reaction, will change depending on several factors, and I've listed them down already here. We have 4 factors. Of course, first would be the substrate, the one which is acted upon by the enzyme, which is the second factor, of course. And then we have 2 additional factors here, which are temperature and pH. Alright, so let's start first with the substrate. Alright, so of course, for each substrate, there should be an enzyme to speed it up here, as we did discuss this topic. So, for example, I have these substrates in blue. I draw 4 of these. And then enzymes, I have 4 also. Alright, so for each of the substrate, there will be 1 enzyme to correspond. So, of course, as in drawing the usual diagram wherein I plot here the concentration of the substrate with the speed of the reaction, alright, the rate of the reaction. The more substrate I put, alright, the faster the reaction would be, alright. So this is what happens. For example, I have this one, alright, this enzyme, this substrate goes to this enzyme, then the other one, then the other one, then the other one. So it follows like for every substrate there's an enzyme, so the reaction would just, the rate would just go up accordingly depending on the number of substrates. But for example, you have these number of enzymes, I only stop with 4, and then I have another substrate here. But this substrate cannot react with a particular enzyme because all enzymes are occupied at the moment. Alright, this situation here is called saturation, because as you can see here, all enzymes are saturated or occupied at the moment, and this additional substrate wouldn't be able to be acted upon by an enzyme. So even if you have a substrate there is no enzyme to correspond with it, the rate would stay the same. So for example, I have this straight line for the first 4. For this one, as I said, the rate would not change, so we expect that this axis would not go up and it will become flat. So the moment it becomes saturated, we will see that as we plot the amount of substrate to the rate of the reaction, we have here a flat line. Alright, so this is the point of saturation. So we could actually enlarge this. They have drawn a larger graph here. Alright, so this is what it looks like again. Alright, so the reaction rate here goes up until we reach the point of saturation, and the rate that we achieve when we have it saturated is called the Vmax, or the maximum velocity, because obviously that is the highest rate that you could achieve given that all the enzymes are already occupied. And one useful parameter that biochemists use is 1/2 of that Vmax, which is here, because for this axis, if you get the 1/2 of that Vmax and then you pull it down and then get the corresponding value for the substrate concentration, you get what we call the Km, or the Michaelis constant. And so the Km would actually give you a certain kind of implication. Alright, what if, for example, I have the 1/2 of Vmax here, and then the Km would be here. So the Km at this point would be lower than this Km, but how much concentration of substrate did we need? Did we need more of it or less of it? Alright, so if you can see here, we just needed less concentration of substrate, and then we get a lower Km, but we got the same 1/2 Vmax. So in short, if you have a low Km, then you should assume that you need just a smaller amount of substrate to reach the same velocity. So that means the reaction is supposed to be faster if you have a lower Km. Alright? And correspondingly, if you have something like this, and the 1/2 Vmax is located here, you get a higher Km with higher amounts of substrate. So here with a higher Km, it means that you need even more substrate to reach the same velocity. So that means the reaction would be lesser in rate or slower if you have a higher Michaelis constant. Alright? So that's it for the substrate. Another term that people usually mention here is the term of turnover number, or the turnover means that it states how much products are being produced by a particular enzyme at the same point in time. So obviously, if you have a higher turnover number, you have more products at the same time. Therefore, the enzyme is more efficient. It generates reactions faster. So higher turnover number means higher rate of the enzyme. So that's it for the substrate. Alright. By the way, you call this curve here a hyperbole, right? It's a hyperbolic curve. Hyperbolic. For the enzyme, it's kind of a no-brainer. If you look back here, if I have this additional substrate, then I just add the additional enzyme. If we have followed the linear kinetics here, following that each substrate will have a particular enzyme, then we should assume that if we have enough enzymes in order to not be saturated, then we will not reach this point. Thus, we would maintain that linear graph. So, given that the substrate will not saturate the amount of enzymes, we would continue to achieve a linear concentration. For the temperature, alright, we would actually achieve something like this. Now, you may be asking why. Alright, you may be asking why. So, at the start, of course, we have a low temperature here, and the rate, of course, would be here. So, remember that enzymes are proteins. Most of the enzymes are proteins, and if there's no heat to activate these enzymes, then they will not really function. So the rate is really down or even zero. Alright? But as you continue to increase the temperature, the enzymes become activated until they reach this certain point. And when you get the maximum velocity at this particular temperature, the temperature that corresponds to this maximum rate would be called the optimum or the optimal temperature, because as you increase the temperature from that point on, the rate would go down and even crash, because remember that enzymes again are proteins, and we should remember that heat or increase in temperature is actually a denaturing agent, and if you denature a protein, of course it would lose its function. Then the enzyme's capability to speed up a certain reaction would falter until it becomes fully denatured, and it will not anymore serve its function here. So it falls down here quickly because it becomes denatured. Alright, and finally with pH. Alright, with pH, so we have here pH and a rate here. There's also an implication with the pH in proteins, right? Remember that pH or changes in pH could actually denature a particular protein. And so, if you have a pH that would denature a protein, if it's too acidic, it would probably denature it. Here, remember, in low pH, we have an acidic environment, and also in a basic temperature, I mean in a basic pH, the protein is also denatured or not in its proper folding. But there would be a certain pH wherein we see that the protein is acting at its best. And so, of course, just with the temperature, the pH where the enzyme acts best or gives the highest rate possible is called the optimum pH. And in extremes of pH, whether it becomes more acidic or more basic, it quickly loses its function. But as a total, we see that here, adjustments in pH would give us here a graph that is shaped like a bell. So typically, when we graph pH versus rate with optimum pH as its peak, we see here a bell-shaped curve. Alright? So these are the main factors that play with the kinetics of the enzymes.